In the last session of Verkada and networks, I gave you a real life example of how different devices can communicate with each other, whether they are in the same subnet or not. And I did mention at the end that although MAC addresses do change every time you're crossing subnets and broadcast domains, that the source and destination IP address will remain the same. But I did caveat it with the fact that sometimes the IP address also changes. And in order for us to understand why this is the case, you have to start reading more about IP addresses. And checking Wikipedia is always a great place to start. And I'm scrolling down here to get an idea of what an IP address actually is. It is a string of 32 bits, ones and zeros, but because we as humans don't really work well with large numbers, we have decided to break them into 4 octets, so 4 groups of 8 bits, and each of those 8 bits will take a value from 0 to 255. So smallest IP address 0000, biggest IP address 255, 255, 255, 255. And although that means that there are more than 4 billion IP addresses, it is actually not enough for all the devices that are currently connected to the internet. There are works to create another protocol that's called IPv6. The address example I gave you is what's called an IPv4 address, but it is very slow to pick up. So in the meantime, we need a way to be able to connect all these devices together using IPv4. In order for this to happen, we'll resort in utilizing what's called public and private IP address. As the name suggests, everything on the internet gets a public IP address. It should not be duplicate, so every single endpoint should have its own public IP address, while within the local area networks that we manage, we are actually using private IP addresses from these 3 subnets. So as you can see here, 10.0.0.0 is indicative of a private subnet, and funny enough, matches the configuration of my router at home, because 10.0.0.1 is the IP address of my default gateway of my provider router. Private addresses, as the name suggests, can be utilized as in any way or form you desire, and most likely there are lots of devices out there in the world that currently have 10.0.0.1. But obviously, if you have 2 devices with the same IP address, you won't be able to route between them. So what actually happens in the background? And this is where I'll be going back to Packet Tracer and to our diagram with our laptop and printer connected at home. And now I'm going to be talking about communicating with the outside world and this particular server on the right hand side. Remember, these IP addresses are summarized in big blocks, and each individual service provider has one or multiple blocks associated to them. And every time they get a new customer, they will associate a new unique IPv4 address to that particular device. So when you get a contract from your ISP, they will send you a home hub. And when that home hub plugs in, it will get a unique public IPv4 address. Afterwards, it will then assign private addresses to any device that's connected downstream, no matter in this example if it's the laptop or the printer. So we need a process somewhere on that particular router to allow us to smartly translate those private IP addresses into the public one that we have in order to make this end-to-end routing work. And this is where network address translation comes in. So this is the ability for the router to substitute the private IP address of the laptop with its own public one when forwarding it to the internet. So actually, from this server's perspective, it's actually the outside port of the router that's talking to it, not the laptop itself. And this is where, if you're asking yourself, well, I actually have more than one device at home, yes, you're correct. That is another challenge, because if you have 10, 20, 30 devices at home, or even in an enterprise, you will not actually get the same number of public addresses. So you won't be able to map them one to one. So we need to utilize a process called port overload that allows network address translation to translate multiple private IP addresses and utilize the same public address. Now, this might make sense if you're looking at the traffic from the local area network. The source IP then gets changed with the router one and then gets forwarded. But what actually happens when the traffic crosses back, right? Because the router will get a bunch of packets. They're all destined theoretically for itself because the destination IP will be its own. But actually, the router will have multiple devices downstream and needs to choose, hey, which device this should go to. And this is where port numbers come in. Remember, we have MAC addresses that allow us to cross a certain broadcast domain. We have IP addresses that allow us to do the end-to-end routing. Port numbers go on top of it in order to allow a device to understand what actual application this traffic is destined to. So for example, HTTPS, which is a well-known protocol that all the browsers use to securely connect to a website, utilizes always port 443. So when a device gets a packet with the destination of port 443, it knows that it actually has to go towards the web browser and no other application. Similar to IP and MAC addresses, you always have a source and a destination port. And in most cases, when it comes to our laptop, for example, connecting to a web page, the destination port will be 443 to generically indicate that this is web traffic, but the source will be a randomly chosen port, and there are around 65,000 options to choose from. And this is very important because, going back to our diagram, although both of these devices will communicate to destination 443, their source ports will vary, allowing the home router to build a table matching them all together. So now when traffic is coming back from the server, it will actually look inside the destination port. Remember, source and destination flip as we're trying to communicate the other way around. And based on that, to know, hey, this traffic is actually coming from the laptop versus this traffic should be going to the printer itself. And that is how, to this day, no matter if you're at home or if you're in the office, we're able to connect so many devices yet not utilize an individual public IPv4 address for each of them. It is the network address translation, specifically what's called the port overload, that allows the router to create a state with all the communication that's going through it. So every time a device across the internet is sending traffic back to it, even if that particular traffic has its own router's public IP address as destination, the router knows, hey, this packet is not for me. Based on the port information, I need to forward this to a certain device in the local area network. And within the packet itself, the router will actually make this translation, resulting in the actual process that I spoke about at the end of the videos. So yes, in most cases, the IP addresses do not change as they cross different hops, but if you're doing any sort of network address translation, they would do so, and purely because we do not have enough IPv4 addresses for all the devices that are currently connected.